Probably people will scream in, but we have to get started. Okay, thank you. Welcome, everybody. Thank you for coming. It's a pleasure to have today Dr. Brendt Wohlburg from Los Alamos National Labs. And Dr. Wohlburg is a staff scientist in the theoretical division of the Los Alamos National Lab. His research interests lie mainly in the area of signal and image inverse problem, with an emphasis on sparse representation and exemplar-based methods. He was an associate editor of the image processing transaction, IEEE image processing transactions from 2010 to 2014, and is currently the chair of the computational imaging special interest group in of IEEE, in the Signal Processing Society, of course, of IEEE, and also an associate editor for the transactions on computational imaging. And it's a pleasure to have him here. And as you know, some of you know that actually we've been working with, my group has been working with Brendt for a few years. In fact, through Eric Scow, who's here also. And anyway, it's a pleasure to have him here to tell us a little bit about these convolutional things in imaging. And thank you for coming.
Thank you, Hamid. I appreciate the invitation. Okay, thank you. As Hamid said, I'm going to be talking about convolutional sparse representations, which is as yet a not very well-known variant of standard sparse representations. And to start with the obligatory outline of the presentation, I was led to believe that not everyone here would be familiar with sparse representations, so I'm going to give a little bit of an overview for those of you who are not, and I apologize if you're an expert and this is boring. And one thing I do want to emphasize is everything I say will be with respect to the synthesis form of sparse representation. So if you use the analysis form, sorry, I'm ignoring you. So I'm going to give an overview, and then I'm going to spend a little bit of time on talking about one of the current state-of-the-art techniques of convex optimization for actually computing sparse representations. And then I'll go on to explain how these representations are used in inverse problems in image processing, which is typically to do it in a blockwise fashion. And that discussion will lead into an explanation of what convolutional sparse representations are and how they relate to the blockwise form. And then I'll take you through the design of an efficient sparse coding algorithm. I think this is important because one of the reasons that the convolutional form hasn't been used much until relatively recently is that it is an expensive problem. And early algorithms were really just prohibitive in cost. And then finally, I'm going to focus on actually using these methods for image restoration problems. And first of all, I'm going to go through a few different technical and practical issues that need to be resolved or that are important in using these methods. And then I'll end, if I get time, with a comparison with blockwise methods, trying to show a comparison of how they perform on the same problem. The reason for this being, convolutional sparse representations have some very nice properties, so it's tempting to just assume that they're naturally superior. But that's not really fair, and I think that the performance comparison is actually interesting. Okay, so just to start with the sparse representations, what they are, it's a simple linear representation where, those are up now. So okay, so it's a simple linear representation where we have a linear operator or matrix, which we call the dictionary, a signal we're trying to represent, represented mathematically as a vector, and a coefficient vector, which is the representation. And it's sparse. We say it's sparse in the sense that most of its entries are non-zero. Okay, and just in terms of notation, we usually write the number of non-zero entries in this norm notation but it's worth mentioning that it's not really a norm. So when people write that, they often put scare quotes around the norm. The reconstruction of the signal from the representation is linear, which is a nice property. Computing the sparse representation in a process that's usually called sparse coding is usually involves solving an optimization problem. And it is, even if it doesn't involve solving an optimization problem, it is a nonlinear problem. The dictionary matrix is usually overcomplete in the sense that it has more rows than columns, and it can either be analytically defined, and this is how sparse representations were used initially. A classic example would be to use an overcomplete wavelet basis, or more recently, the representations are actually learned from data in a process known as dictionary learning. Okay. So how to formally formulate the sparse coding process? The most natural way of doing so is a problem like this, where we have some accuracy of representation threshold epsilon, and we want to represent our signal within that tolerance and find the sparsest representation that does so. Unfortunately, this representation is generally intractable, and there are two broad classes, completely different broad classes of techniques for trying to solve a problem like this. The first one is heuristic algorithms for computing approximate solutions to this exact problem with the L0 norm. A good example of methods there is matching pursuit and orthogonal matching pursuit. And the second class is convex relaxations of this problem, where we replace the L0 norm with the L1 norm. And these methods are motivated by some nice theory that shows that under certain conditions, the solution to this problem is actually the same as the solution to that problem. And for the purposes of this talk, I'm going to be discussing methods using this form, which is essentially a penalized form of that problem. I call it basis pursuit denoising for historical reasons. Many of you may be more used to it, described under the label of the lasso. Okay. And let me add, I don't think I mentioned this in the beginning, this is a small audience. If you have any questions, please feel free to stop me during the talk and ask. So, as I said, this is what we're going to concentrate on, and it's actually a relatively difficult problem to solve, primarily because the L1 norm is not differentiable at 0, and because we're trying to find sparse solutions, a lot of our solution does lie around 0. There's an enormous list of algorithms that have been proposed for solving this problem. I'm going to look at one that is, I don't want to start an argument, but it is either the state-of-the-art or one of the state-of-the-art methods for solving this problem, called alternating direction method of multipliers. And many of you are probably familiar with this algorithm, or this technique, but I'll just briefly run through it, just because, number one, I'm going to need this background when we switch to explaining algorithms for the convolutional form. And number two, even if you don't do sparse representations, it's an extremely useful optimization framework to be familiar with. And the general form of problems that ADMM addresses look like this. It's the sum of two functionals on different variables with a constraint linking those variables. And there's some very interesting theory here I don't have time to explain, but ADMM solves this problem in a set of 3 steps, one of which involves the first functional and a term here that looks like an L2 measure on the constraint violation, plus what we call the dual variable. Then the second step is essentially the same for the second G functional here, and then finally what's called the dual variable update, which I'm sorry I don't have time to explain. This method has some very nice properties. Convergence can be guaranteed under mild conditions, and it really does work well for a wide range of problems. If you look at the literature, you will see just an enormous range of problems that people address using ADMM. And if you're not familiar with it, I highly recommend this really good tutorial by Boyd et al. That has made a major impact and in spreading the use of ADMM. Okay, so let's look at how we use ADMM to solve the basis pursuit denoising problem. This is our problem. And the first step is to apply what we call variable splitting. So we introduce an auxiliary variable y, which we insert into the second term here. And then we apply a constraint that x equals y. And it's not difficult to see that this is an equivalent problem. And it's also not difficult to see that this is a special case of the general ADMM form that I showed on the previous slide with these substitutions. Okay. And if we apply those substitutions in the ADMM iterations I showed on the previous slide, we end up with a system to solve looking like this. And the ADMM algorithm essentially involves repeatedly iterating over solving these three equations. The first, I'll just go through these one by one. The first one is easy mathematically, or no, not necessarily computationally, in that it is just the sum of two L2 norms. So we can actually compute the solution as this linear system. And this can be a big linear system, but there are a few tricks that can be applied to solve it more efficiently, the most important of which is that this parameter rho here, which I didn't mention before, is called the penalty parameter. It's essentially an algorithm parameter for ADMM, and it determines the convergence rate. If we keep it fixed, the left-hand side of this system stays the same during our iterations. So all we have to do is, it costs a bit to factorize it, LU or Cholesky once, but after that, in each iteration, the solution can be computed extremely efficiently by exploiting that factorization. Okay, and then the y update has the form shown there with a little substitution to simplify. And this is one of the reasons that ADMM and other proximal methods have become so widely used for sparse representation problems, is that that problem can actually be solved in closed form. This is what's called the proximal operator of the L1 norm, and that's relatively computationally cheap to solve, typically called soft thresholding. Okay, so in summary, ADMM decomposes the basis pursuit denoising problem into three steps. We have a large linear system. That's not mine. My apologies. Then we have the y update, which can be solved in closed form by the shrinkage operation. And then we have the dual variable update, which is just trivial arithmetic. Okay. Okay, so now on to using these representations in particular image representation, but the specific interest is inverse problems. If the dictionary has a fast transform, because it's analytically defined, a good example being wavelets again, then it's completely trivial to apply these techniques to an entire signal or image. And in fact, this is what was done when sparse representation techniques were first applied to signal and image processing problems. But as I mentioned initially, it's become more popular now to learn the dictionary from data. And in that case, the dictionary is usually represented by an explicit matrix. And when we do that, it's just completely intractable to apply the sparse representation, either the dictionary learning or the sparse coding in the ambient space of the dimensionality of a full signal or image. And the usual solution is to cover the image with an overlapping set of patches and compute the sparse representations completely independently over each of those patches. And this is what's typically done in sparse representations, and they have achieved very good results in a huge variety of inverse problems. And a particularly good example where it works well is denoising of images subject to Gaussian white noise. But there are some inconvenient aspects of this representation. And the two of the major ones are, because the sparse representation is computed independently on each of the patches, when we look at the representation on the image as a whole, it's not optimal for the image. In particular, it's less sparse than it need be because it's not globally optimized. And the other aspect of this is because of the overlapping patches, we end up with multiple estimates for each pixel. And in some cases, one ends up having to make relatively ad hoc choices in how to combine them. In some cases, for example, Gaussian white noising again, just averaging them is the principal thing to do. So this is not always a problem, but it can be inconvenient. Okay. So this diagram illustrates the point I just made. I'm doing it in 1D to avoid taxing my diagram making skills. So here we have a signal that's been covered with 3 overlapping blocks. And each of those blocks is pulled out as a separate signal, and then completely in the sparse code, the sparse representation here is estimated independently on each of them. And as I said, what one might argue that what you really want to do is a global optimization to get a more efficient representation. And this is what the global optimization with the same basic dictionary would look like. So again, I've got the same D, but now I've put it in a block form in a single matrix. And this optimization is it's essentially finding the same representation structure as on the previous slide, but jointly optimized so that when we sum the coefficients chosen on each of these shifted dictionaries, they collaborate to represent the signal instead of doing so separately. So in particular, just to give an example here, if there's a structure in this part of the signal that can be represented by, that needs to be represented in that block or in that block, because we're doing them independently, both blocks will go ahead and use coefficients to represent that structure. Whereas in the second form, with the joint optimization, they'll collaborate. One of them will end up taking the task of doing the representation, and one of them won't. So we'll end up with what is potentially a much sparser representation.
So is there any rationale in choosing your blocks, though?
I'm getting there.
Okay, sorry.
Yes?
Is X a concatenation of other 3? What's the mechanism of this X?
So this S is the same as the other one. The X ends up looking somewhat different. But let me flip back and forth. See, the S is actually the same size. So I'm representing the same signal. It's just the representation has a different structure. The X, right. So the X ends up, it's not just a concatenation, it's sort of an interleaved concatenation. Okay. But just for simplicity, I showed a large block step there, but we typically want shift invariance, and we'd like a 1-pixel step. So what we typically prefer to do is just shift the block down by 1 pixel at a time. And now, let's look at the first element in the subdictionary D at each location, right? So that's in red, and now we can see that's occurring at 1-pixel intervals in this dictionary here. And of course, that's just reminiscent of convolution. And it turns out that if we apply the same argument to each atom in the subdictionary D, that this large explicit block matrix structure here is exactly equivalent to this convolutional form here. The convolutional form here, where we just take each atom and convolve what I like to call a coefficient map here, and then sum it with all the others, this structure, modulo boundary effects, but that can be taken care of too, is exactly equivalent to this structure. The only difference is you end up, essentially these representations here are re-indexings of this large representation here, but that's the only difference. And as I said, this form here is what we call a convolutional sparse representation. Okay, just some background. These were introduced in the neural network community inspired by the convolutional neural networks that have become so well known. And the first paper that introduced this idea actually introduced them within a neural network architecture as well, with multiple stages, and referred to it as a deconvolutional network instead of a convolutional network. The next slide, I'll look at the difference in more detail. Something really worth emphasizing here is, although under the name convolutional neural networks, this is a relatively new idea. They've only been around for 5 years or so. There is an equivalent idea called translation invariant sparse representations that's much older, 10 or 15 years. And interestingly, if you look at the convolutional neural network literature, at the convolutional sparse representations literature, only until very recently was it even recognized that these are equivalent to an old idea. So essentially two completely separate streams of research that only just converged. I think I mentioned earlier, this convolutional sparse representation form is still not very widely known and not widely used, but there are indications over the past 2 years that interest is rapidly growing in using them for inverse problems. And I think a major reason for them not being used for imaging inverse problems in the past was the computational cost of the algorithms. If you look at earlier papers, even 3 or 4 years ago, the size of images that people apply these techniques to are really small, 64 by 64, maybe 128 by 128, so really tiny. Okay, I promised to explain the distinction between a deconvolutional network or convolutional sparse representation, which is one layer of a deconvolutional network, and a convnet. And it really is just an analysis-synthesis dual question. The convolutional neural network is an analysis representation in that we have an input image, we convolve it with a filter, and that gives us a feature map. And the deconvolutional network is a synthesis representation. I have an input image I want to approximate. I convolve my coefficient map with a filter and adjust the coefficient map so that it approximates the input image. Okay, so let's look at formally how we solve this, how we do the sparse coding, and how it relates to the standard sparse coding problem. This is what I like to call convolutional basis pursuit denoising, and you can see it's very similar to the standard form, except that now instead of a linear operator and a vector, I just have the sum of a set of convolutions. And just for notation here, I'm going to use n to denote the size of the signal, or the number of pixels in an image, m for the number of filters, and L for the number of coefficients in the filters. And the earliest algorithm for solving this, again, in the convolutional sparse representations literature, it gets more complicated if we look back to the translation invariant literature, solved this in the spatial domain, and the cost was m squared n squared L, which, as you can imagine, is a major impediment to using it for large images because of the squared on the number of pixels. More recently, Bristow et al. Proposed a frequency domain ADMM algorithm, which has had a major impact because this was the first work that really spurred the recent development in improving the computational cost of these methods. But it had a computational cost of order m cubed n, so it's order 3 in the number of filters, but at least it's linear in n. And in any reasonable context, that's going to be much faster than the spatial domain algorithm. And what I'm going to show you over the next few slides is that one can actually do substantially better than the m cubed n. Okay, first some notation. So all I'm doing here is introducing some block matrix notation. First of all, I introduce an operator D that is just the operator that performs the convolution, and block matrices and vectors that allow me to write the convolutional form back in the standard basis pursuit denoising form. It just simplifies the algebra a little. And if we recall the ADMM iterations for the basis pursuit denoising problem, now that we're using the same high-level mathematics, we end up with the same, at a high level, what looks like the same problem. And even when we implement the algorithm, these two updates essentially are the same. They don't cost any more. They're easy to do. The one that poses problems is this one, the X update. Its form is the same, but now D transpose D is Mn by Mn. So it's absolutely huge. So just simple-mindedly trying to apply the same techniques as you would apply in the standard case is not going to end in a happy state. Okay. So since the D's involve a set of convolutions, the natural thing to do is to take this into the frequency domain. So if we take this into an equivalent frequency domain problem, where now D hat is just the diagonal of the FFT of the filter, we end up with a solution that looks like this. And now we've got D Hermitian transpose D in the frequency domain to deal with. It's the same size as the spatial domain one, so we can't attack it directly, but it has structure that we can exploit for an efficient solution. And let's look at that structure. So D hat consists of a set of concatenated diagonal blocks, and the notation here is the subscript on the D indicates which filter I'm using, and the value in parentheses indicates the frequency index for each filter. And the fundamental point that helps us here is that if we look at the cross product, if we look at D Hermitian transpose D, there are no cross products that mix frequencies. We mix filter indices, but there's no mixing of frequencies. So that means that what was one enormous Mn by Mn linear system to solve actually decomposes into N much smaller M by M linear systems, which makes this much more tractable. But one critical question remains is, how do we solve these smaller linear systems? And the initial paper that pointed this out used direct methods for solving them, factorization, Gaussian elimination, etc. And that's where the order m cubed in the computational order comes from using direct techniques. And this is faster than the spatial domain solution, as I said, but it can be very slow. And some of the problems are, remember when I discussed the ADMM solution for the standard sparse representations, I pointed out that we can make it much more efficient by caching factorization in the matrices. The problem is now we just have too many matrices to make it feasible to actually cache all the factorizations. So that's one trick that we just can't use. And the other problem is because we're calling a direct solver for each of these n linear systems, it's very difficult or impossible to construct a vectorized implementation. So we have to actually use some explicit outer level loop, which actually has a huge computational impact. And as I said, the cost is n m cubed. So if we want to use really large dictionaries, which people sometimes do, it grows very fast. So to construct a more efficient solution, let's look at one of these subsets. So to go back here, let's pull out the subset for one frequency index like that, which, as I said, these are independent. So that's the smaller linear system for one frequency index here. And the critical point to notice is that we can factorize this linear system in this form. And that's a rank 1 matrix plus a scaled identity. And once you recognize that, it becomes obvious what to do. Just apply the Sherman-Morrison formula. And with a little bit of re-indexing, to simplify the notation, we end up with the solution looking like this. So we essentially have a closed form expression to solve that inverse, that linear system. And if we do it this way, we end up with order nm squared instead of nm cubed. So we've already taken it down to quadratic, But we can actually do better than that, because the n squared is because this product is a matrix. But if we reorder the operations, we can get to this form essentially just by attaching the A Hermitian transpose to the B here. We can reorder so that we only have vector operations. And that takes the computational cost down to order nm. So we've taken it down from nm cubed to nm, which can make a huge difference. And now it turns out when we do that, the computational cost of solving this x step is actually dominated by the FFTs. In other words, mn log n, which good luck trying to improve that. Okay, some empirical evaluation of how much difference this actually makes. This is what the execution time for this solver is depending on the dictionary size. And up here is the Gaussian elimination solution. The next two are conjugate gradient solvers with different error tolerances. And down here we have the Sherman-Morrison solution. And the last one here is the cost of a single FFT, just put in for comparison purposes. Now, to be fair, since we're comparing execution time, these methods differ in their solution accuracy, so it's only fair to compare what we get for these different computational costs. So this is the corresponding solution relative residuals for the execution times on the previous slide. And you can see the cost of the actual error we get on the Sherman-Morrison solution is intermediate between conjugate gradient with a 10 to the minus 3 and a 10 to the minus 5 threshold. So one might argue that this is not particularly accurate, but one of the nice properties of ADMM is that each step does not have to be solved to particularly high accuracy, and usually a little bit better, 10 to the minus 3 or a little bit better is perfectly adequate for good convergence. So there's no point in wasting all that computation getting it down to machine precision like Gaussian elimination. Okay, so on to the last major section of the talk, which is using these techniques for image restoration. And I'm going to start with just running over some of the advantages, or at least what seem to be advantages, of the convolutional sparse representation form when we're applying it to imaging inverse problems. And as the point I really made repeatedly when I introduced the relation between the blockwise and the convolutional form was that the convolutional form ends up with a much more efficient representation in terms of sparsity, because the representation on each subblocks collaborate to give the representation rather than just being computed independently and then averaged. The shift invariance is an advantage. You'll see this in early sparse representation techniques, for example, where cycle spinning was introduced into wavelet denoising because the shift variance I seem to have lost my...
Yeah, you're still on.
Okay. Is it going to come back automatically, you think?
Yeah, sure. It's back.
Okay. 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 So shift invariance is useful. A property that can be convenient is, as I mentioned, that we get a single-valued representation. So instead of a lot of independent representations that have to be aggregated somehow, each pixel has one estimate when we reconstruct. And in many problems, this just makes the process of posing the inverse problem much more natural and simpler. And a final point I haven't made is that in standard sparse representations, a few people have tried to construct multi-scale dictionaries. And they've come up with some very nice ideas, but it really is difficult to do in standard blockwise sparse representations, just because the multi-scale nature is incompatible with this, or at least semi-incompatible with this blockwise nature. In contrast, in the convolutional form, multi-scale dictionaries are absolutely trivial to implement and use, because there's just no constraint that all of our filters be the same size. Okay. As I said, this is not yet widely used for image restoration problems, but over the past 2 or 3 years, there have been some very interesting works on using these techniques for inverse problems. And there's some nice examples now where these techniques give state-of-the-art results in some well-known problems. For example, super-resolution image fusion, structure-texture decomposition. There's some work on tomography, dynamic MRI reconstruction, and most recently, range streak removal. And one thing I want to emphasize is the convolutional form is not always superior to the standard form. And an interesting example is what's arguably the simplest inverse problem in image reconstruction, which is denoising of images subject to Gaussian white noise. It appears that at least the standard form of convolutional sparse representations are inherently inferior to the independent block form. And I suppose this shouldn't be too surprising, just in the sense that the averaging of overlapping estimates is just such a natural thing with this problem that one shouldn't be too surprised that it's difficult to beat. And in a paper that's currently under review, we investigate this a bit further, and it turns out that if you compare the two side by side and try and make a fair comparison of what's happening, as you might expect, the convolutional form has a lower bias in its estimate in the denoising problem, but it ends up having a much higher variance, essentially because the convolutional dictionary is very overcomplete, so the sparse coding problem is quite unstable. Okay, so now I'm going to spend most of the remaining time going through some technical issues that either one will encounter and must be dealt with, or that can be useful when trying to actually apply these methods in practice. And the first of these is low frequency or large scale components in the signal or image. Now, anyone who's used standard sparse representations will be, at least for image reconstruction problems, will be used to this idea that one subtracts the block mean or the DC component from the block before doing the sparse representations and then adds it in at the end. Now, it turns out that this issue occurs in the convolutional form as well, but while it's an optional step that can improve performance in the standard form, it's essential to take care of it explicitly in the convolutional form. Unfortunately, we can't just directly translate the pre-subtraction of the DC because the blocks aren't being independently represented. So that solution isn't an option. And one can think of the generalization to the convolutional form of subtracting the DC component as doing a high-pass filtering stage. In other words, instead of subtracting the DC of the image, you subtract the low-pass component of the image. And as I said, performance will be very bad if one doesn't do this. And there are essentially 3 options for how to deal with these large-scale or low-pass components. The first one is, as I said, we can do a high-pass filtering. Typically, you do a low-pass filtering, subtract that. The residual is what gets sparse coded, and then that low-pass filtered component gets added on at the end. This isn't always even feasible. There's some problems, for example, in painting or impulse noise denoising, where either the pixel values are not known or they're subject to outliers. So if we do just a simple linear pre-processing, those distortions are going to be in the low-pass component. So that's going to give a very bad solution. In some cases, one can get around that by doing a non-linear filtering step. For example, one could do total variation denoising instead of low-pass filtering to compute the large-scale estimate of the large-scale component. But that's not always the best solution. For a substantially different way of doing this is instead to build the task of representing the low-pass component into the optimization. And there are two different ways of doing that. One of which is just construct a large smooth filter like a Gaussian and add that to the dictionary. And then solve the sparse coding problem with this additional filter in the dictionary. And the low-pass component will essentially be that filter convolved with its coefficient map. And an important point here is that filter must decay to a good approximation of 0 at the boundary. If it doesn't, the discontinuity at the boundary ends up acting like a discontinuous window function, and one ends up with the spectral response of this window function dominating the spectral response of the filter, and it creates very nasty artifacts in the reconstruction. And then the final solution, which I think in many cases is the best choice, is that we can actually include an additional impulse filter in the dictionary, and then we add a smoothing term to the entire problem. And we notice I've introduced weights here, because what I want to do is I want to adjust these weights so that the smoothing term is only applied to my impulse filter. I typically don't want to smooth the rest of my coefficients that are estimating a representation of the high-frequency image components. And here, I don't want to subject my impulse to the L1 norm. So getting good performance here really critically depends on using these weights. And fortunately, it turns out that there is a way of extending the efficient solution in the frequency domain that retains the efficient Sherman-Morrison solution I explained to you. It just essentially, instead of let's see if I can get to it without too many steps back. So whereas before, here we end up with an identity. Now, when we're solving the problem with the smoothing term, that ends up being a diagonal term rather than an identity. So it's very marginally more expensive to solve. Okay. Now, I'm going to touch on topics now. I'm running low on time. As I mentioned, the ability to use multi-scale dictionaries easily is a really nice advantage of this technique. And this is an example of one. This dictionary has 3 different size filters in it. And the table here is just a basic illustration of some of the advantages of the multi-scale. What this is different dictionaries, all of the same number of filters, used to sparse code separate testing data from the data on which the dictionaries were learned. And one can see the functional value, if we take that as meaningful as a measure of how good the dictionary is. In each case, the dictionary that has multiple filter sizes has the lowest functional value. Okay. Another issue that comes up in practice in solving inverse problems is boundary handling. And one of the concerns that was initially expressed with using frequency domain solutions is if we solve the problem in the frequency domain, we automatically have circular boundary conditions. And as we all know, in many imaging problems, that can cause artifacts at the boundary and is undesirable. And there are a few different ways of dealing with this. The simplest is just to do boundary extension like symmetric extension. So you do a symmetric extension, solve the problem on the symmetrically extended image. If you've symmetrically extended far enough, the artifacts should occur in the extended region, and at the end, crop out the extended region. It's not very elegant, but in practice, it seems that in many cases, it gives as good performance as the more careful boundary handling methods. The next approach, so the next level of complexity, is if we recognize that one of the main problems with the circular boundary conditions is that we have filters that straddle the boundary and wrap around to the other side of the image. which are obviously not going to give a realistic image model, what we can do is just constrain the representation so that any filter that crosses is going to cross the boundary is just forced to 0. So that even though those filters are possible, we've just removed them from the representation. And this can be reasonably effective, but it doesn't completely solve the problem because we've essentially made the representation available at the boundary less rich than the representation in the center. In the center, there are many filters that can represent a particular pixel, whereas on the boundary, there can be only a few. So the most correct way of doing the boundary handling is to actually zero pad the image and the coefficient maps, and then, zero pad them to just the right amount so that a filter can never actually cross from the coefficient map into the padded region and then back again on the other side into a virtual copy of the main region. And together with this padding, we need to solve a masked form of the sparse coding problem that looks like this. So we introduce this mask matrix here because we want to mask out the padded region from the data fidelity term. I have a few slides on this, but I think I'm going to skip them. The point here is that you can't just directly insert this mask matrix into the efficient frequency domain solution I showed you because it doesn't, it's a spatial mask. It doesn't have a compact representation in the frequency domain. But it turns out that there are two entirely separate ways of actually making minor changes to that solution that do introduce that mask matrix. Okay, I will skip those. Okay, the next topic is, okay. So the next topic is multi-band images. I'm going to largely talk about color here, but this would extend to multispectral, for example. And the interesting thing here is that other than the work I'm going to talk about, no one has really considered this thus far, but it's an important problem because obviously one wants to apply these techniques to color images. And I'm going to look at 3 different ways of computing a convolutional sparse representation on a multiband image. And the first and most obvious one is just to do it on independent bands. But as we know, if we treat the bands of a color image completely independently, we typically get poorer performance than if we actually model the correlations. The next one is to compute a separate representation for each band, but couple them with a structured sparsity term. And then the final one is our dictionary actually gets a multi-channel characteristic. So the first one, just the independent bands, it's a trivial extension of the problem for a single band. The problems decouple, so it's absolutely straightforward to solve. The second one looks like, so this is the independent one. The second one, the functional we solve looks the same, except that we introduce an additional term here, which is what's called the L21 norm, that in this case is being used to promote what's called joint sparsity. In other words, we want on each band, at a particular position, we'd like the supports in the different color bands to be at least approximately the same. The idea being that in images, edges tend to occur at the same place in the different bands. And it turns out that this is extremely easy to add to the efficient solution. So it's an absolutely trivial change. I will skip this. And then the final one is to actually introduce a color dictionary. So now, in the previous case, maybe I should actually emphasize this. So here I have a single channel dictionary, and each band, there's a different coefficient map for each filter and for each band. If I go to the color dictionary, now there's a single coefficient map for each filter, but each color band has a separate filter in the dictionary. And it turns out that solving this problem actually gives a fundamentally different structure. I won't go through it in detail, but essentially we end up with a linear system like this to solve for the X step. And unfortunately now, instead of a rank 1 system plus a scaled identity, we end up with a rank C system where C is the number of bands. So this is a fundamentally more difficult problem to solve. It turns out, though, that if we have relatively few bands, such as a color image, a very easy way of doing this is, instead of doing a single step of the Sherman-Morrison solution, we can just iteratively apply the Sherman-Morrison solution. And it is, for a few bands, it's cheap and very effective. If one has more bands, such as in a hyperspectral image, that's not the best solution, but there are other efficient approaches one can apply. Okay, so this is interesting. This is a single band dictionary learnt on a set of grayscale images. If we initialize the color dictionary learning using this grayscale dictionary, we end up with this color dictionary, where one can clearly see roughly the same structure, but now there's actually multi-channel information in the filters. Okay, I will skip over some of this. This is just a performance comparison comparing the 3 different methods. And as one might expect, this is an in-painting problem. The independent band approach is quite substantially inferior. What's interesting is that the joint sparsity approach on separate bands actually gives slightly better performance than the color dictionary. I would warn, though, I'll skip the rest of this. These should be considered preliminary results. It is possible that this is not because the joint sparsity approach is inherently superior. It could just be because the color dictionary learning process is more difficult. So the color dictionary I used may be slightly inferior. Let's see. Okay, I will skip this and wrap up since I've reached the end. Okay. So just to wrap up the material I've gone through, convolutional sparse representations have a number of advantages over the standard form. In particular, the single-valued representation is very convenient. Just to belabor the point, the representation is more efficient. The translation invariance of the representation is useful. And the ease of constructing and using multi-scale dictionaries is a substantial advantage that I should add hasn't really been completely exploited yet. The convolutional form often leads to simpler problems, both in terms of formulation and actually writing the code to solve them. And the problem is still expensive. I'm not going to argue that one can go out there and do a convolutional sparse coding on a 4K image in real time, but the situation is much better than it was a few years ago. And if anyone is interested in actually playing with some of these techniques, I have both MATLAB and Python libraries available at this URL that include most of these, I think essentially all of the algorithms I've spoken about today, as well as convolutional dictionary learning. I would add, if anyone is interested in using these, I would recommend the Python library over the MATLAB version, just because it's a real programming language. It is under more active development, and it just allows more flexibility. So, thank you.
We have time for some questions.
You want to give a word about online dictionary learning in the convolutional case versus online dictionary learning in the patch case?
Sorry, what was the first part of the question?
The online dictionary learning in convolutional versus patch. what's the advantage of, can you do online learning in the convolutional case?
Yes. In fact, we have a paper submitted to ISIP on exactly that. I don't remember, was this something we discussed with you? Okay, yeah. So the natural thing to do is adopt the online dictionary learning techniques from the standard sparse representations case, where there's this approach that has essentially an accumulator array that allows one to accumulate the effect of the learning from the previous images without storing the previous images. The problem with just doing the direct translation is that this accumulator array ends up being huge. But there are some techniques one can apply to control that. So yeah, it still needs some development, but we have that working.
I apologize in advance if this is a dumb question, because I'm not a subject matter expert.
There are no dumb questions.
If you go back a few slides to the performance graph you had with the 3 different methods for dealing with the color bands.
Sure. I seem to be going the wrong way.
I was wondering if you were to just convert the color image to a grayscale, how you would anticipate the performance. So I guess it would be kind of similar to the...
Oh, you mean what would the performance be on a single, on a grayscale? That's a good question. I mean, I guess it would be the independent. Well, yeah, that would be my guess. So the problem is that it's not just convert to grayscale, because you have to specify how you convert the problem to grayscale, right? Because there are different corruptions in different channels. So when you convert to grayscale, do you keep all the corruptions, or do you do an and or an or on the corruptions? So it's a non-trivial comparison, but I would guess the independent, but depending on how one did it.
Okay. I was thinking that the joint method is kind of like a more sophisticated way of converting it to a single channel, where you're looking at weightings from the different color bands.
It's sort of a soft way of converting it. You keep the separate representations, but you penalize them for being different, rather than forcing them to be the same. Yeah.
Just converting it to grayscale.
Right. Yeah. Okay, I see what you mean.
Yes. Well, Larry Perry and Duke of some other, they use also dictionary learning, but not in this format.
Yeah, no, they use a Bayesian framework.
Yes, exactly. My question is that, is there a comparison between these two? Because that also computation is quite intensive. They show wonderful results, but that requires a lot of art in order to achieve that.
That's a good question. The sad thing is that these two communities don't talk much, right? We each go our separate ways and don't compare our techniques. So it would be very interesting to compare, but I very much doubt anyone has.
But these are two different things, so it might be hard to compare fairly, because it's two totally different.
I guess one could choose a problem, right, and let each one be optimized for its best performance.
Yeah, another thing, I think I heard that you mentioned that. In comparison, there's something called a basis mismatch.
I'm not familiar with that.
Oh, okay. Basis mismatch, basically how you choose the base matrix. I think you use A or you use D, something like that. That choice may affect the quality of image.
Oh, very, very, very heavily.
Yeah.
I mean, sure. I would describe that as falling within the dictionary learning process, right?
Yeah,
how one learns the dictionary. Yeah. Oh, certainly. That's having the right dictionary or a good dictionary is absolutely critical, and that comes back to my comment on that the color dictionary gives slightly worse performance here, but the learning process is more difficult. So
Yeah.
it may just be that dictionary just wasn't quite as good.
May also be related to the filter I use it.
Sure.
The filter some filter may be sensitive to noise, some may not.
Yeah.
Any other questions? Yes.
So is there a particular reason that you choose ADMM for the optimization over the other optimization?
Yes. I have compared, are you thinking of FISTA in particular?
I think it's 1 over t squared. Then what about ADMM in this cost function?
But the problem is, what's the actual computational cost of each step, right?
So per iteration computation, ADMM will allow you to do faster.
I have actually done performance comparisons. Unfortunately, I can dig them up somewhere afterwards and show you. Between ADMM and FISTA, and in ADMM, so in ADMM in the X step, you actually really want to solve the linear system, right? Whereas in FISTA, you're computing a gradient. So in ADMM, there's no question you want to do it in the frequency domain, because solving that system in the spatial domain is just terrible. In FISTA, there's more of a choice. Do you compute the gradient in the frequency domain or the spatial domain? My experiments show that computing the gradient in the frequency domain is actually substantially faster. I mean, it's not the same sort of enormous difference that you would have in ADMM, but it's faster. And I have compared FISTA in the frequency domain with ADMM in the frequency domain. And interestingly, there's some types of problems. For example, just plain computing the sparse representation with a large regularization parameter, where ADMM and FISTA give about the same convergence and about the same total computation time. But there are other problems where ADMM is just vastly faster. FISTA just seems to take a very long time to converge. Yeah.
I actually have a very quick question, particularly on this slide here. Have you also looked at the variational approaches to in-painting? I mean, this problem has been sort of also looked at from a variational point of view, using like PDEs.
Oh.
Yeah.
My understanding is that the PDE methods for in-painting tend to be very good at getting structure right, but they're poor with image content like textures, which is why the more recent exemplar-based methods for in-painting have become popular. So one important point I skipped over, relevant to your question, is this is not what I would consider a real in-painting question. This is what I call in-painting with quotes, because in my view, real in-painting is you have a large contiguous missing region, and then you would attack it with these variational methods.
Right.
Whereas here, this is more like a sort of an impulse. It's sort of an impulse noise problem where you know where the noise is, and it's a much easier problem. But I think it's a useful problem as a test problem for regularization techniques and image models. I don't think it's a particularly useful problem in its own right.
But it's interesting though, because here you're not actually accounting for the governing law of the noise at all. In other words, how is the noise distributed? How does the noise distribution impact, and how does it come in? How does it factor in into your? Because I mean, your regularization basically is through the L1 thing. But does that really,
Yeah, no, that's a good point. It's not.
Is that really optimal vis-a-vis the underlying noise?
Yeah.
All right. Let's thank our speaker again.